Hello, welcome to the third session in Python Foundations. My name is Wesley. If you haven't watched the previous two sessions, feel free to watch those before diving in. Today's session, we will focus on functions in more depth. We've seen them previously and used them, for example, the append function for lists and the even more general print function and the length function, len. Here, we'll dig into how you can make your own functions to encapsulate code that you will reuse over and over. So, writing our own functions. All right. And we're going to review a little bit from the previous lesson. We discussed lists, dictionaries, and flow control. Lists are ordered collections of data that can be used to hold multiple pieces of information while preserving their order. We use square brackets to access elements by their indices, and they start at index 0. All things that operate on lists, like slices, use the concept of an inclusive lower bound and an exclusive upper bound. So the following gets elements in the list mylist with index values of 0, 1, and 2, but not 3, right? Question 1, slicing. What other way is there of writing the same statement using slicing? Hint, think about leaving out one of the numbers in the slice. So what we're getting at here is you could leave out the number 3 to grab all of the elements starting at index 0 up to the end of the list. Dictionaries are named collections of data that can be used to hold multiple pieces of information as values that are addressed by keys, resulting in a key to value data structure. In other words, key value pairs. They are accessed with square brackets, just as we did with lists, but dictionaries are initialized with curly brackets, right? So my dict is equal to, we're using curly brackets to initialize, and then going ahead and seeding some key value pairs, cake, tasty, toenails, gross. Notice that each pair is separated by a comma, and then the key and value is separated by a colon. Finally, we talked about flow control and using the concept of conditional execution to decide which code statements were executed. To recall the figure, the diagram here on the left is an if statement, the diagram in the center is a loop, and the diagram in the right is just a sequence of code blocks that we might call. And each block could be represented as a function. So to move on, functions. For loops let you repeat some code for every item in a list. Functions are similar in that they run the same lines of code and frequently for new values of some variable. We call these parameters. They are different in that functions are not limited to looping over items. Functions are a critical part of writing easy-to-read, reusable code. We create a function like the following. We have our reserved word, def. This indicates to the interpreter that we are going to begin defining a function. We then have our function name, and then in open parentheses, whatever parameter we're going to make accessible to the function, and then a colon. Notice that we start our indentation, and anything in the indent contains the operation that our function performs. We also have with it between, we'll recognize this from our first session, but these triple quotes, this is what we call a doc string, and it informs our coder what this function is meant to do. We then have the meat of our function, and then finally a return statement. Anything that appears after the return statement will be returned by the function. All right. To call the function, we simply type in the function name followed by whatever parameters are necessary for the function to work. So I've got my function print string. I'm going to put in the parameter gix is awesome, and then it just prints it to the output of the cell. So reserved words, def, return, and yield. Notice the highlighted words in our function definition, def and return. These are reserved words in Python used to define functions. Every function definition requires these reserved words. Yield is another reserved word that is similar to return but operates slightly differently. It is beyond the scope of what we are covering in this session. This tutorial from Real Python has good information on the topic. So what is return doing in this function? I've got def, my squares, the function name, takes in a parameter a, and then returns a double asterisk 2. That double asterisk is how we raise exponents in Python. So this is going to be a to the power of 2. Return is going to output whatever values follow after the keyword return when we call upon our function. So here the output of my square will be 4 because 2 squared is 4. If I change this to 3, it'll be 9. If I change it to 4, it'll be 16, 5, 25. Could do this all day. Actually, I'd probably stop at 9, 100. I'm going to return 2 values. So we can return as many values as we like in a function. We simply separate them with a comma. So here I'm going to take what I previously defined as my square. And instead of returning the a to the power of 2, I'm also going to return a as well. And we see how the output updates accordingly. We can capture these values on the output by assigning them new variable names, right? So here I haven't assigned them to anything, but in this line I'm returning them and assigning them to the variable name square and then new a. And then I can print them, right? Square and new a. Global versus local variables and function parameters. In a function, new variables that you create are not saved when the function returns. These are local variables. Variables defined outside of the function can be accessed but not changed. These are global variables. Let's define the following function. I've got my little func, takes in a parameter called a, assigns a value of 10 to a new parameter called b, and then returns the multiple of a and b. So I'm going to feed in my little func 2. 2 times 10 is 20, and so the return is 20. If I run the following, I'm going to get an error message, and this is because b was defined locally within the function, but not globally. Let's play with this a little further. Now let's define b outside of the function and call our function with a equals 5. What happens here? We see that b is still 100 instead of 10 as it's defined within the function. This is because b inside of my little func is a local variable. It doesn't matter how I define b outside the function because within the function it is set locally. Let's try this a little bit more. So I'm defining my new func a. Notice that b is not declared within the function, but it is accessing the value of b. Now, if I call on my new function, because b is not defined locally within the function, it takes on the global value. This is extremely important to remember for notebook environments because you can inadvertently break your code when you exit the notebook. This is not happy, happy, fun, fun behavior for us. We want to be explicit about how we define and use our variables. There are some exceptions to this rule, but we'll not get into them here. So let's just simplify this. We'll do b equals 1,000. Now, because I'm not defining b within my new func, we by default have to take on the global value. And so we're returning a, in this case, times 1,000, right? So we get a times 1,000, a is 5 to receive 5,000. And notice that we can still print b within the function, it just takes on the global value 1,000. So the way I had this written before in scientific notation is also just useful shorthand in Python. If we want to do something times 10 to a power, we just type E3. So this will be 1 times 10 to the third power. Function parameters. Parameters or arguments in Python are all passed by reference. This means that if you modify the parameters in the function, they are modified outside of the function. An enrichment topic below is that we go over exceptions to this. In the following example, I've got a new function called changeList. It takes in a parameter called myList. Right? And I have a little doc string here that describes the function for me. This changes a past list into this function. So it's going to change a function it's going to change a list that's been passed into the function. Right? And here's where the change is being made. We're appending the string value of 4 to the list. We're then going to print the list inside the function and then return nothing. So to test this function, I'm going to have myList 1, 2, 3. We're going to print my list before the function. We're going to call the function and then print it after. So notice that because I passed in my list into the function, our function was able to edit that value globally. All right, I have an enrichment topic here that will discuss some exceptions to this rule, and you are free to peruse it as you see fit. But we will move on to parameter types. All right, we will now discuss the following parameter types. Function calling. So we're going to break this up into function calling and function writing. On the calling case, we have positional and keyword parameters. A positional parameter appears like this. We have our function name and then the parameters separated by commas. All right. So we're inferring what parameter is being assigned by their position. This is where the word positional comes from. The second type of parameter when we're calling a function is a keyword parameter. And this looks like the following. I have my function name, and then as I assign values to parameters, I'm going to use the parameter name with an equal sign. So A is going to take on a value of 10. The parameter B is going to take on a value of 20. Notice that I could also write it this way with B coming first and then A. Because I am using the keyword, we can swap the position of each parameter. It doesn't matter, right? Because we're being explicit about the assignment. Now, taking the function writing case, in function writing, we can specify default values for parameters. So in this case, I'm defining a new function called func, and I'm assigning default values to the parameter A as well as the parameter B. You can contrast this with non-default values where you have a parameter A and a parameter B, but no equal sign, so no default value. Let's take some examples. I'm defining a new function called printName. It's going to take two parameters, first and then last. And notice that first doesn't have a default value, but last does, and its default value is my last name, Beckner. The function is going to print your name is, and then the values first and last. Notice I'm using a new syntax here for my print statement. I've got curly brackets where I'm going to insert any variable that I like. And then after my string, which is surrounded by double quotes, I do dot format, and then the list of variables that are going to be passed into where those curly brackets appear. Some people like to write it this way. Some people like to write it in the f-string format that I introduced in the previous session. It's really just a matter of preference. All right, I'm going to run this cell. Your name is Wesley Beckner. Great. Let's play around with the above function. Notice here I was able to swap last and first because I'm using a keyword, right? So I could also write it this way. And it runs the same exact way. Let's check out this. So here I'm using Wesley as a positional argument and then a keyword for the last parameter, for the parameter that has the name last. So it's okay to have a keyword argument follow a positional argument, but not the other way around. And this would make intuitive sense because the positional argument becomes ambiguous when it follows a keyword argument. All right. Functions can contain any code that you put anywhere else, including if, elif, else, for, and while loops, as well as other function calls. And we've already seen this because we were using print within our function. All right, to just give a quick example, def print name age will take in the parameters first, last, and age. It will print the first and last name, and then print your age is. Notice yet another way I'm writing my print statement here. The %d is indicating that I'm going to put in a number value here, and then I assign the number with the % appearing after the string, and then the parameter value. And then I'm going to write a condition. If age is greater than 25 and age is less than 40, print you're a millennial. I'll have to update this as the years go by. All right, as you see, your name is Wesley Beckner, your age is 29, you are a millennial. This is already out of date. I'll not reveal how I'm 30. There we go. The scientific Python stack. So before we move on to the second set of topics for today, which is debugging, I want to talk briefly about the scientific Python stack. In addition to Python's built-in modules like the math module we explored previously, there are also many often used third-party modules that are core tools for doing data science with Python. Some of the most important ones are NumPy, or numerical Python, and which this contains tools for efficient manipulation of arrays of data. If you have used other computational tools like IDL or MATLAB, NumPy should feel very familiar. SciPy, or scientific Python. This contains a wide range of functionality for accomplishing common scientific tasks such as optimization, minimization, numerical integration, interpolation, and more. We will not look closely at SciPy in Python Foundations, but we will use its functionality at some points later in either data science foundations or general applications of neural networks. Pandas, labeled data manipulation in Python. Pandas is short for panel data and contains tools for doing more advanced manipulation of labeled data in Python. In particular, with a columnar data structure called a data frame. If you've used the R statistical language, and in particular the so-called Hadley stack, much of the functionality in Pandas should feel very familiar to you. Matplotlib, visualization in Python. Matplotlib started out as a MATLAB plotting clone in Python and has grown from there in the 15 years since its creation. It is the most popular data visualization tool currently in the Python data world, though other recent packages are starting to encroach on its monopoly. Some of these are Plotly, Altair would be another one. Scikit-learn, machine learning in Python. Scikit-learn is a machine learning library. It features various classification, regression, and clustering algorithms, including support vector machines, random forests, gradient boosting, k-means, and dbscan. The library is designed to interoperate with the Python numerical and scientific libraries NumPy and SciPy. Scikit-learn is an amazing library to learn machine learning. Okay, I just wanted to briefly mention those to give a heads up on where we're headed. For the rest of today, in the second part of our session, we're going to focus on debugging. All right, on to debugging. It's always important to check that our code is, quote, plugged in. In other words, that we're actually exercising the problem that we think we are. Every programmer has spent hours chasing a bug only to realize that they were actually calling their code on the wrong dataset or with the wrong configuration parameters, or are using the wrong version of the software entirely. Mistakes like these are particularly likely to happen when we're tired, frustrated, and up against a deadline, which is one of the reasons late night or overnight coding sessions are almost never worthwhile. I took this from Software Carpentry. So visit that link if you would like to read more. And in fact, I'm going to take a lot of my debugging outlines from Software Carpentry today. We'll now dedicate some discussion and practice to debugging in Python. This easy to overlook topic can save us oodles of time down the road. It's worth the investment. Borrowing from Software Carpentry, we'll highlight the key guidelines to debugging code. 1. Know what it's supposed to do. 2. Make it fail every time. 3. Make it fail fast. 4. Change one thing at a time for a good reason. 5. Keep track of what you've done. And 6. Be humble. We'll get into what we mean by each of these. But before we get started, we will refer to writing tests, and specifically writing unit tests in this module. Don't worry too much about the specifics of unit tests for now. We will have a dedicated module for that. What we do need to talk about is a specific built-in function in Python called the assert function. All right, the assert function. Let's take a simple example of the assert function. If I wanted to test that the sum of two numbers is correct, I could write the keyword assert, and then my expression, so sum, 2 and 5 equals 7, a comma, and then whatever I want to be sent as an error message to the user should my condition evaluate to false. All right, nothing is sent to the printout because our condition is satisfied. If, however, we run sum 2 and 4 equals 7, we will get this error message. Assertion error should be 7. Now, to make this a test, we'll want to wrap it in a function. So I'm going to make a new function, right? I've got my reserved word def, and then test underscore sum, and then my assertion statement. And I can either have my print accessed outside of the test function or within it. I'm going to move this to within. And so because my assert evaluated true, all is well, and the successful message is printed to the screen. Note if I change this to sum 1, 2 equals 6, we get our error message. Assertion error should be 6. So assertion messages are useful ways to write little functions that test our code. Let me change this back. All right. Just to reiterate, our test above failed because the sum of 1 and 2 is 3 and not 5, or not 6 rather. We get a traceback that tells us the source of the error, right? Our assertion error. It tells us the message that we wrote after the assert statement. And we also get this little stack trace that shows us where the error occurred, right? On what specific line of code, and then even which function was called that caused the error. These are super useful diagnostic tools for us that we should familiarize ourselves with as we get used to Python. We will worry about the intricacies of what to test and when to test it at a later time. For now, we just need to understand the assert function so we can practice debugging and writing short tests for the problems that we fix today. Okay. So, going through now those 6 or so steps that we outlined earlier. Know what it's supposed to do. This may seem obvious, but it's easy to recognize that an error is happening without knowing what the correct answer is. This makes unit tests especially handy. They force us to know the expected outcome, at least for intended use cases. Here are some tips in regard to knowing the expected outcome. Test with simplified data. Test a simplified case, compare to a base model, and then visualize. Next, make it fail every time. It can be extraordinarily difficult to debug code that is predicated on some stochastic process. Remove stochasticity, that is randomness, when possible. For instance, seed your random value generators with random.seed or np.random.seed. We'll talk about each of these when we get to the random library and the NumPy library. 3. Make it fail fast. A corollary to this is narrow down the source of the error. And again, this is why we write unit tests before we write integration tests. If it takes 20 minutes to train your neural network, and the error occurs during some post-processing plotting of your loss history, obviously don't retrain the neural net each time you iterate over the failure. Along the same lines, if you're debugging something in a for loop, run the loop once or run the intended code outside of the loop with a placeholder for the iterated variable in order to test and debug the code. 4. Change one thing at a time for a reason. Not much nuance here. Just like it's a good idea for us to change one aspect of our machine learning models and track the performance rather than to change multiple things at once, it's better to change one feature when debugging at a time. Changing multiple things at once creates interaction effects that can complicate the whole problem. 5. Keep track of what you've done. This is where Git and GitHub come in handy. It's so incredibly easy to forget what you've done, and weeks or even days later from the time you first encountered the bug, forget whether you fixed it, did a temporary fix, and or what you did to fix it. My tip: if you're working in a Jupyter notebook, something I do is write at the top of my notebook my to-do items. I then strike through items I complete and update my notes for the next time I work on the code. Similarly, I name my notebooks to reflect and categorize what they are about. Primarily, I have test_something.ipy notebooks and prototype_something.ipy notebooks. 6. Be humble. Lastly, ask for help, take breaks. A week of hard work can sometimes save you an hour of thought. I directly stole that quote from Software Carpentry, and I love it. A week of hard work can sometimes save you an hour of thought. So rest your mind. All right. Exercise: debug a short code block. Again, remember, you can pause the video to work on this your own if you would not like to see my solution. Your friend is writing a function to calculate BMI. They are concerned that seemingly all the patient's values have the same BMI, despite having different heights and weights. Determine the bugs in the code, then write a unit test for the function calculate_BMI. All right, so let's take a look at this. I've got patients here. It's a list of lists. The first item, it says, is the weight in kilograms and the height in meters. So I got someone who's 70 kilograms, 80 kilograms, and 150 kilograms, and then 1.8 meters, 1.9, and 1.7 meters high. I've got my calculate_BMI function. It takes in the weight first and then the height. And it looks like somebody wrote a little code comment here that tells me what the calculation should be, which is the weight divided by the height squared. All right, so this math looks okay, right? I've got weight divided, and then I've got even some parentheses here to make sure that my power operation is on the height in the denominator before the division is performed. All right, that looks okay. Now I've got 4 patient and patients, so I'm going to loop through each of these items. Remember, each pair is a weight and height pair. All right, do we see an issue with this line? It looks like we're trying to access patients, right? But we're looping through patients. Why would we want to access it? In fact, we actually just want to grab patient. So I'm going to go ahead and delete this. Patient should be the pair of weight and height. So weight and height looks right. That's the proper assignment. And then I'm sending this to the calculate BMI function, which expects weight first and then height. Look at here. I'm feeding it height and then weight. That's going to perform an error. I could either swap these or I could assign them using What was the word? A keyword argument, right? So I'm going to use keyword arguments to make sure that the proper assignment is happening. And I want this to be like this, right? Weight is weight and height is height. All right. And I have a little unit test here down below to test whether this is operating the right way, right? So I have, this is a nice note here. This is how we want to test our code. We have the true answers, we have the true input values, and now we can write an assert statement. So let's practice that. I'm going to delete pass here. Remember, pass is just a placeholder, signifying that we expect something to be done in the future. So I'll do assert patience. Oh, we want to call our function that we're testing, correct? So we'll do that. We'll do for patient in patients. And then we'll just take our for loop here. Right, so this gives us our BMI. And then we can check and see that these round to the proper value. See if we got, so it looks like round is going to be, let's actually test this. Maybe we don't know this. Let's see if round is something that we can do in Python. Let's do 103.2. All right, you see, we've got this special function in Python. And let's pretend I don't know anything about it. I'll just type round, open parentheses. My tooltip will tell me it expects a number and then the supports round. So this is going to be the round a number to a given precision in decimal digits, right? So it expects the number and the number of digits we want to round to. So what I'm going to do is I'm going to round the output of BMI to how many decimal places? 1, right? And I'm going to set it equal to BMIs, but I want to set it equal to the proper BMI, right? So one way we can deal with this is I'm going to introduce another useful tactic in Python, enumerate. So enumerate is going to not only loop through patients, it's also going to give me an index. So now I've got two variables that I'm going to capture here. I'm going to capture the index and the item or element rather within the list that we're currently indexed at. So now I can use that IDX to access BMIs correctly. And our assert statement will go here. So we'll assert that the rounded value of BMI from our calculation is equal to the stored true values. And then we need to pass a message if this is false. Something went wrong. Oh no, we got something went wrong. Let's figure out what's going on here. So the way we like to do this, we'll pull this out. And then let's just print BMI. Let's print round BMI. All right. Let's print round BMI is equal to BMI's IDX. BMI's is not defined. We'll have to pull, remember, local variable here. We'll need to define it globally now that we're outside the function. All right, so we've got a true, a false, and a true. What is the deal? So the second BMI, 22, oh, check it out. We have 2 decimal spaces here. So how do we want to deal with this? All right. It just so happens that when we round to 2 decimal places, the rounding is such that we actually cut off the second decimal for the first and last stored value. So if we want our assert statement to work correctly now. We just need to change this 1 to a 2. And there we go. And again, I'm going to move this print statement to within the actual test function. So now it's all contained. And when I run test calculate BMI, we get a success. Awesome. So that is it for today's session. Going back to the course website, we'll see that there is an associated lab for today, as well as a project notebook. So we'll briefly look at those before we hop off. Here we've got some practice in our third lab with basic function writing, finding unique elements in a list, computing factorials, and then even using recursion to compute a factorial. Or we have an example of using recursion to compute a factorial, and then using recursion to solve our Fibonacci sequence from lab 2. And there's a little summary in here of what recursion is for you to look at. We also have a project file associated with today's lesson. In this project sequence, we're going to be building tic-tac-toe with vanilla Python. And we're going to break it down into very digestible steps. So for this part, we're going to be building an interactive tic-tac-toe game that you can run in the Jupyter Notebook. Cool. That's it for today, and thank you for tuning in.